All right, well, let's move on to develop one more extremely important aspect of electromagnetic radiation. And as I said before, if I take a steel plate and I elevate it to some temperature T, I can calculate the power coming out of that plate. That's simply equal to the area of the plate times the Stefan-Boltzmann constant times the temperature of the plate to the fourth power. But if I plot that intensity against wavelength, I have this very characteristic shape. And that very characteristic shape is called the shape of blackbody radiation. And we'll see why it's called blackbody radiation in just a moment. But blackbody radiation marked one of the most important transitions in modern science. And that transition occurred because during the 19th century, the crown jewel of scientific development was the understanding of electromagnetic radiation and the fact that it's a wave and that you can calculate the behavior of it by a set of equations called Maxwell's equations. The problem was that in the analysis of blackbody radiation, if we apply Maxwell's equations, we have a relationship between the radiant energy, which is what we've called the intensity, against the wavelength. If we calculate that with Maxwell's equations, we have a relationship that looks like that. It increases dramatically as we go to shorter and shorter wavelengths. But when we measure the output at a fixed temperature, the curve looks very different. It actually descends back to zero at very short wavelengths. And this has a famous name. It's called the Ultraviolet Catastrophe. That's a pretty shocking description for something in science, but it turns out it was a major problem at the turn of the century, that is around 1900, the turn of the 18th to the 19th to the 20th century. And this was completely outside the understanding. Nobody could explain how this could possibly happen, how the crown jewel of mathematical descriptions of electromagnetic radiation could fail in such a simple experiment. The experiment involved a cavity, and this cavity could be made out of any material. We could make it out of chromium, steel, carbon, plastic, and the remarkable thing was that the emitted intensity I as a function of wavelength was completely independent of the material. It had nothing to do with what that cavity was built from. We have exactly the same relationship between intensity and wavelength, no matter what the material. That meant that the characteristic electromagnetic radiation inside that cavity didn't care about what the material was. And by the way, the term blackbody radiation, which is the famous way in which this radiation is described, came from the fact that these cavities were built as a sphere with a tiny, tiny hole in it. There's a pinhole, and it meant that if a photon went in, or if light went in, it didn't come back out. And so that's why it's called black, because it absorbs any incoming light. But it was Max Planck. He was very young at the time. I think he was about 26 years old. And he looked at the functional dependence of this blackbody radiation, and he recognized that it looked very much like the distribution of molecular velocities in a gas, which Boltzmann had solved. And Planck came up with a hypothesis. His hypothesis was that light isn't a wave, it's a series of particles. But more than that, the energy of each one of those particles of light can be simply expressed as a constant times the frequency of that radiation. So nu is the frequency, and epsilon is the energy of a single particle of light. name for that particle of light is the photon. Now, when Max Planck published this, it's one of the most remarkable stories. He didn't believe it. He said, I grew up studying electromagnetic radiation. I grew up studying Maxwell's equations. That was the crown jewel of 19th century physics. And here I'm proposing that light is not a wave, it's a particle. And so, but he said, I have to look at the experimental evidence. If the experimental evidence doesn't match the theory, there's a problem. And this is the scientific approach. That is, you hypothesize, you test it against observation, you modify the hypothesis, you finally come up with a theory. But he said, I can't accept this ultraviolet catastrophe without coming up with a solution. And when I propose that light is comprised of particles, I come out with exactly the right expression for the relationship between intensity and wavelength. And in fact, when he published this, not only did he question it, nobody believed him. And finally, as we will see subsequently, it was work by Einstein and different experimental techniques that proved that Max Planck was in fact correct. A number of years later, so this was 1900 when he made this hypothesis. By the 1920s, it was an accepted fact that light has both wave properties and particle properties. And Max Planck, given the fact that he was very young when he proposed it, and when he proposed it he said, look, I'm young enough, I can make mistakes. Of course, this hypothesis and the identification of the photon turned out to transition us from classical physics to modern physics. It was that transition. And in the 1920s, Max Planck mentioned the fact that a new scientific truth does not triumph by convincing opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that's familiar with it. And this is a profoundly important dynamic in the evolution and development of scientific ideas.